Good morning, students. Myself Vaidegi, working as assistant professor in Sri Muthukumaran Institute of Technology. Today the video lecture is from the subject CEC 334 Analog IC Design for 6th semester ECE students. Welcome to this lecture on feedback and single stage operational amplifiers. In this session, we will discuss single stage and two stage operational amplifiers, input range limitations, gain boosting techniques, slew rate, power supply rejection ratio, and noise in operational amplifiers. These concepts are important for understanding the performance of analog integrated circuits. First, we see about the introduction to operational amplifiers. An operational amplifier or op-amp is a high-gain differential amplifier widely used in analog electronic systems. It amplifies the difference between two input signals. An ideal op-amp has infinite gain, infinite input impedance, and zero output impedance. Although practical op-amps do not achieve these ideal values, they are designed to come as soon as possible. Next, we see about the single stage op-amps. A single stage op-amp contains only one amplification stage. Its circuit structure is simple, making it easier to design and analyze. Single stage amplifiers consume less power and can provide faster operation due to fewer internal stages. However, the voltage gain achieved is relatively limited compared to multi-stage designs. Next, we see about the two-stage op-amp. To achieve higher gain, engineers often use a two-stage op-amp architecture. The first stage is usually a differential amplifier that provides initial gain and good common mode rejection. The second stage further amplifies the signal and provides output driving capability. Two-stage op-amps are widely used in integrated circuits because they offer high gain and improved overall performance. Next, single stage versus two-stage op-amps. Let us compare the two architectures. Single stage op-amps are simpler, consume less power, and offer faster response. However, their gain is limited. Two-stage op-amps provide a much higher voltage gain and better output drive capability, but require compensation techniques to ensure stability. Therefore, the choice depends on the application's performance requirements. Next, the input range limitations. An important parameter of an op-amp is its input common mode range. This range refers to the range of input voltages over which the amplifier operates correctly. If the input voltage exceeds this range, some transistors may enter saturation or cutoff, causing distortion and loss of linearity. Designers must ensure that the input signals remain within the specified range for proper operation. Next, we see about the gain boosting. Gain boosting is a technique used to increase the effective gain of an amplifier without significantly increasing power consumption. This is commonly achieved by adding auxiliary amplifying circuits that increase the output resistance of certain transistor stages. Higher gain improves accuracy, precision, and overall amplifier performance, especially in integrated analog circuits. Next, we see about the slew rate. The slew rate is defined as the maximum rate at which the output voltage can change with time. It is expressed in volts per microsecond. If an input signal changes faster than the slew rate limit, the output cannot follow accurately, leading to distortion. Therefore, the slew rate is particularly important in high frequency and large signal applications. You can mention SR is equal to dV0 by dt. This equation represents the slew rate, which is the rate of change of output voltage with respect to time. Next we see about the power supply rejection ratio. Power supply rejection ratio or PSRR measures how effectively an op-amp rejects fluctuations in its power supply voltage. In practical systems, supply voltages may contain noise and ripple. A high PSRR ensures that these variations do not significantly affect the output signal. Therefore, higher PSRR value indicates better performance and improved signal integrity. Next we see the noise in op-amps. Noise is an unwanted electrical signal that affects amplifier performance. Common sources include thermal noise caused by resistor temperatures, flicker noise which dominates at low frequencies, and short noise associated with semiconductor devices. Noise reduces signal quantity and can limit measurement accuracy, particularly in sensitive instrumentation applications. Next, how to reduce the op-amp noise. Several techniques can be used to reduce noise. Selecting low noise operational amplifiers is the first step. Proper grounding and shielding help minimize interference. Filters can improve unwanted frequency components, while careful PCB layout reduces noise coupling between circuit elements. These practices improve overall system performance. Finally, we came to the conclusion of the lecture. To summarize, we discussed the architecture and characteristics of single stage and two stage operational amplifiers. We examined input range limitations, gain boosting techniques, slew rate, power supply rejection ratio, and noise sources. Understanding these parameters helps engineers design reliable and high performance analog systems. Thank you for your attention. Hope you all understood. Thank you.